So in this video, we're going to talk about another application of differential equations or exponential functions, and this is going to be what's called exponential decay. And again, what we're going to do is we're going to start by looking at a differential equation, which is dp dt is equal to minus kp. In this case, k is greater than 0. And so in this case, instead of having just dp dt equals kp, we have a minus kp, which means that when I write the general solution for this is going to end up being p of t is equal to p naught e to the minus kt. And the most common application of exponential decay that we'll look at is what's called radioactive decay. So when you have a material that's what's called radioactive, what you have is you have some material, and then after a certain time it gets to half of that material. So let's say the initial amount is A0. That's our initial amount. Then after one half-life, it's called, we get to 1/2 of A0. And then after another half-life, which we'll just call HL, we're going to get to half of A0, which is going to be 1/4 of A0, and so on. So what we're going to find is that we can use basically the same principles that we used for exponential growth or the growth equation and apply this up here, and this is what we'll call the decay equation. Okay, so let's look at how this would work in an example. Let's say that what we have is we have a material has a decay rate of 2.8% per year. And what we want to do is we want to find how much will remain after 70 years. So here's what we're going to do is we're going to start with our decay equation, which we'll call dn dt, and that's going to be minus 0.028n. So this right here is what we're going to call the decay rate. And that's just taking 2.8% and turning it into a decimal, which gives us 0.028. So what we can say is that the amount of substance that we have, n of t, is equal to n naught e to the minus 0.028t, just like we saw on the last slide. And really all we have to do now is plug in 70 years for t. So we have n of 70 is equal to n0 e to the minus 0.28 times 70. And let's say that we have an initial amount of 1,000 grams. Then what I would do is I'd say n of 70 is equal to 1,000 e to the minus 0.028 times 70, which if I plug this into the calculator gives me 140.9 grams. So basically the process is exactly the same. What we're going to do in this case is just use a negative in our exponent, and that's going to indicate that we have an e raised to a negative power, which we know is going to be exponential decay. So let's say that what we wanted to do is to find the half-life. Then the way we would do this is we would say that n of t is equal to n naught e to the minus 0.028t. And what we could do is we could say that at the half-life, I have 1/2 n naught equals n naught e to the 0.028t. And what I'm going to do is I'm going to cancel out these n naughts on both sides. So I have 1/2 is equal to e to the minus 0.28t. Now what I want to do in this case is I want to solve for this t right here. So what I'm going to do is a trick that is taking the natural log of both sides. So I have the natural log of 1/2 is equal to the natural log of e to the minus 0.028t. And if you remember, we have this property of logarithms that says that if we have something raised to a power like this, then we can move the power out in front. So I have the natural log of 1/2 is equal to minus 0.028t times the natural log of e. We also saw a property that said that the natural log of e is just 1, because this is asking what number must I raise e to get e. So this here is going to be 1. So I get the natural log of 1/2 divided by minus 0.028 is equal to t, which in this case, again, if we were to plug this into the calculator, we would end up getting that this is about 25 years. So for half-lives, we have a special equation given the decay rate. So if k is the decay rate, then we can say that t is equal to the natural log of 2 divided by k, and this right here is the calculation that gives us the half-life t based on the decay rate. And again, this will be something that is useful for your quiz and also useful for your test, but more importantly, it's something that you should know, which is that when we're trying to solve these equations, which are called exponential equations, that have the variable in the exponent, which in this case the variable is t, we're going to use this trick right here where we take the natural log of both sides, which allows us to put the exponent out in front right here, and then we multiply that by the natural log of e, which is going to be 1. So that's a way that we solve for a variable that is in the exponent in order to figure out when it's in the exponent of something that has a base e.